Okay, hi everyone. So this is Aspen Plus tutorial number 3. So let's go over this together. So in this tutorial, we're going over some problem solving tools, specifically on how to use the sensitivity analysis and how to use the design specs in Aspen Plus. And if you read this tutorial, basically what we're trying to do is you have a reactor and you have some cooling. The exit from the reactor is at 420 degrees Celsius and I need to cool it to 150 degrees Celsius using a heat exchanger, and the utility available to me is water at 95 degrees Celsius and 1 bar. I pump it to 20 bars, and then the water at 20 bars is what I use in my heat exchanger. It passes through the heat exchanger, it exits at 360 degrees Celsius, which is basically steam, and I use this steam to run a couple of turbines to generate some energy, and then condense it and recycle it. So as you can see here, the problem is that we don't know what the discharge pressure of turbine 1 should be. And clearly anything between 1 and 20.5 bars would theoretically work. The question is, which is best? So we need to basically find the best discharge pressure, or the discharge pressure that will leave turbine 1 in this type of scenario. And the strategy is as follows. We're going to create a model in Aspen Plus for the steam plant. We're going to use a model with a design spec to figure out how much steam we need to achieve both at 360 degree Celsius steam temperature and 150 degree Celsius hot outlet temperature. So I need to set a design spec to achieve these two metrics right here. Then I'm going to complete a model, determine how much power is produced for one specific gas, and use sensitivity analysis to vary the pressure and temperature, determine how the power produced changes with the intermediate pressure. Okay, and you have some assumptions here. So assume for now that we know that 200 megawatts of cooling is needed to take the reactor effluent from 40 degrees Celsius to 150 degrees Celsius. So basically this means that we can use a heat stream to model the heat transfer without needing to model the reactor effluent or the reaction. So basically what this means is that instead of modeling a reactor and modeling a hot stream, I'll just assume that I need to remove 200 megawatts out of this heat exchanger, and this should be sufficient to cool the stream from 420 degrees Celsius to 150 degrees Celsius. And then Aspen Plus does not handle processes that are completely in a single loop, like the stream cycle. Therefore, we need to break the loop and adjust, and just make sure that the broken pieces match. And this a thing with Aspen, Aspen Plus at least. So if you use the advanced, or if you use the other form of Aspen Plus, which is Aspen HYSYS, which is what you would encounter in industry, you can usually deal with the recycle by adding something called a recycle block, which sorts out the iteration or the calculation. But with Aspen, whenever you have a recycle, I need to break it here and then just keep running the simulation until the results in this stream match the results in this stream. We're going to have a look at it in a second. But when dealing with recycles in Aspen, you usually need to break this stream and just rerun the simulation a few times until two ends match. And then once they match, you can connect it and run it. Otherwise, Aspen will have a hard time finding a solution. So therefore, with these two pieces of information, our model for the purpose of Aspen Plus should look like figure 3.2. So this is the model we're going to generate in Aspen in a bit. And let's address the simple question of how much water should be in our steam loop. Specifically, we need to find the amount of water that provides 200 megawatts of cooling while exiting the heat exchanger at 360 degrees Celsius and 20.5 bars. So I have water at 20.5 bars entering this heat exchanger and exiting at 360 degrees Celsius. And we need to basically find out how much water, or the flow rate of water, which will remove 200 megawatts from this heat exchanger and exit at 360 degrees Celsius at the same time. So we don't know the flow rate. You can play around and try like a random number, maybe it will work. However, in Aspen, you can set a design spec and it will calculate it directly for you. So first, start a new model. So we're gonna follow these instructions now. From here, first start a new model in Aspen Plus. I suggest you making sure your units are set to met C bar. Okay, so I'm gonna switch to Aspen Plus from here on. And then you can You can follow along from the tutorial if you have it printed out, or if you can go back and forth, whichever is easy for you. Okay, so now I'm sharing the Aspen Plus screen. You just double check, okay. And basically, first step, we're gonna start a new model, and we're gonna set the units to met C bar. So again, to set the units, you have to be in the Properties tab. Bottom left here, Properties tab is the first one, and the units usually under Setup, Specifications, and I'm gonna set it to met C bar. So it's already under set as met C bar, so that's good. You can give your simulation a title, of course, you know, if you like housekeeping, you know, good housekeeping practices with your file, you can always call it, you know, tutorial 3 or, you know, heat exchanger, whatever it is, whatever you want. Okay, so let's go back to the tutorial. Since we're going to use only water, use Steam NBS as the physical property choice. Okay, so we have two pieces of information here. Compounds, our only compound we're using in this tutorial is water. So I'm going to write H2O. I'm going to press tab and make sure that it has water here. If you don't see water in these basically columns, it means something's off. So maybe you want to find it and search for it. So we're going to set water as our component. And then under methods, we're going to use Steam NBS as our equation of state. And this is the recommended equation of state if your only chemical is water, as in this case, right? You only have water. So we're going to use Steam NBS. And as you can see, Steam NBS is not in the common methods. So I need to click here, and I'm going to select all to show all the methods. And then I'm going to scroll down and find Steam NBS, which is right here. Okay. So I selected my method to be Steam NBS. Good, so now let me go back to the tutorial and see what the next step is. Create a model of the process from streams 1 to 3. So let's go back to the tutorial here for a second. So you're being asked to create a model of the process from streams 1 to 3. So basically I just need to replicate this part starting from here all the way to here. So I'm gonna have a pump and a heat exchanger in the first step. Okay, so let me go back to my Aspen Plus simulation, and I'm gonna go to simulations here. And for streams 1 to 3, basically I need to just create a pump and create a heat exchanger. Okay, so let's do this. So I have pressure changers here, I have a pump, and exchangers, I have a heat exchanger. You can use, you know, if you like this icon, you can use it. Whatever you want, just be careful, you know, when dropping units in Aspen Plus, it's always a sticky sort of drop. So if you have this plus icon, you need to click on escape. Otherwise, you're going to end up adding an infinite, or you'll just keep on adding units. Okay, so I'm going to add a material stream here, and I'm going to rename this 1. So let's rename this as 1 just to match the thing. And I'm going to rename this guy pump. And then I'm going to connect the material stream from the exit of the pump to the inlet of the heat exchanger. And again, always be careful that it connects. If you see an error here, or if you see an error in the heat exchanger, it means that you did not connect the stream properly. And I'm going to have an exit stream from the heat exchanger. And again, you always have this plus, click on escape to get your normal mouse button back. I'm going to rename this 2. And I'm going to rename this 3. Okay, one thing in the tutorial, we said that we're not going to model the reactor effluent. We'll just add a heat stream for 200 megawatts. So let me go back to the tutorial just to remind you of what I'm talking about. Basically this stream right here, right? It's 200 megawatt heat stream from the tutorial. And in Aspen, you can create heat streams in a similar fashion to creating mass material streams. So if you see here on the left of your model palette, this is a material stream. If I click on up, I can get a heat and a work And in this case, we're interested in heat. We're not interested in work. And work is separate from heat. So work, when you have a motor, or you have, a turbine, you get work. But if you have a heat exchanger, you have heat. And I'm going to basically add a heat stream here. So I'm going to click here for the start and here for the end. And this heat stream, let's just call it reactor heat, okay? So it doesn't like having a space, so let's just call it reactor underscore HT. Doesn't like semicolon, so let's call it reactor dash HT, and this is called reactor heat. And let me rename this heat exchanger as well. Let me call it hex 1. Okay, so it's heat exchanger 1. Let me zoom in a bit. So this is my process so far, or this is the process which I created. So I have a heat exchanger, hex 1. Let me move this guy here. I have a material stream going into a pump, then going to a heat exchanger, and then the exit of the heat exchanger. And I have a queue. I'm entering the heat exchanger. Okay. So now let's define the conditions for this simulation, right? Let's go back to the tutorial and see if they have any specific instructions. Okay, create a model of the process from streams 1 to 3. We did this, right? And then assume no pressure drop across the heat exchanger. In order to build this model, you'll have to add a heat stream of 200 megawatts, which feeds into the heat exchanger. And then to do this, you go to material icon and hit the drop down and select it. Note that the heat stream is just a model. So this is what we did. So we're gonna add 200 megawatts. And then you're being asked when you add the heat stream. Okay, so let's just follow the instructions. Let's go, let me go back to the simulation here. So if I double click on Q on the stream, and you can always work from the tree on the right hand side. I'm gonna set it at 200. And then here I'm gonna set it as megawatt. So 200 megawatts for my heat stream. For my heat exchanger, we said that we want basically our pressure drop to be 0, right? And that's enough really for the heat exchanger. And for the pump, if you go back to your tutorial and you look at figure 3.2, we want the exit from the pump to be at 20.5 bars. So this is what I'm doing. The discharge pressure will be 20.5 bars, okay? And basically this is the setup for these blocks, for these two blocks here. Okay, and one thing when dealing with heat exchangers, so you can set, if you don't, for a heat exchanger, if you want to set the pressure drop to be 0, you can do it in 2 ways. So if I click on the heat exchanger, and if you later on, if you're using it and you feel confused, what does pressure drop parameter mean or pressure drop correlation parameter mean? You can always click on pressure and set it to 0, and this will do the same thing. This will set your pressure drop to be 0. So either option would achieve the objective of having a 0 pressure drop across a heat exchanger. And a 0 pressure drop across a heat exchanger basically means that if a fluid enters here at 20 bars, it's going to exit at 20 bars, right? Usually processing units, you have a pressure drop across it. So usually in a realistic situation, my pressure here is 20 bars and I put it across a heat exchanger. Depending on the size of this heat exchanger, it's going to lose some energy as it flows to the heat exchanger, as it passes through the bends of the heat exchanger. and it will exit at a lower pressure. So this is in a realistic case. But in our case, we're just assuming that the pressure drop is 0. Okay, so now let's see what's the next step. Okay. So if we go back to the tutorial, I just want to point something out mentioned in your tutorial here. It's important. So notice also that when you connect the heat stream to the heat exchanger, that uses one of your degrees of freedom. Therefore, when you go into the heat exchanger and specify the pressure drop, the other drop-down box is disabled, right? What this means is that, when dealing with heat exchangers, typically we need to specify two pieces of information, right? A pressure and a temperature, a pressure and temperature change, whatever it is. However, in this case, we can only give it one piece of information because there is only one degree of freedom, and the other degree of freedom was satisfied by adding this Q here, right? So you already implied the temperature change across the reactor by adding this heat stream. So I only need to specify the pressure drop across the reactor. This is just something important to remember, that whenever you connect a Q to a heat exchanger, you only need to specify one more, give it one more piece of information for Aspen to be able to solve this simulation. Okay. So now let's just see if the model works for the first few parts. Guess a water flow rate of 14,000 kilomole per hour. Okay, so let me go here. And here I'm gonna guess a water flow rate of 14,000 kilomole per hour. Right, and we need to set a pressure and a temperature. So let me go back to the figure 3.2. So we want the water to enter at 95 degrees Celsius and 1 bar. So let me go back to my simulation. So I want it to be 95 Celsius and 1 bar. And let's run the simulation and answer questions. The first few questions. So why is it not happy here? 14,095 Celsius, 1 bar. Let me click on next. Component flow, fraction, or concentration must be specified. Okay, it's fine. So let me specify the fraction here. Mole fraction to be 1 of water. And hopefully this satisfies the stream. Enter. Here we go. So now this is blue, so now it's good. Okay, let's run the simulation and let's answer questions 1, 2, 3 in your tutorial. So let me have a look here. Okay, so question 1 in your tutorial says for a guessed water flow rate of 14,000 kilomole per hour, what's the temperature in degrees Celsius of stream 3? If done correctly, it should be in the 390 to 410 range. Okay. So let's go here. And the results are available. So let's have a look at the temperature of stream number 3. So again, to look at the results, you go to the bottom here, look at streams, and you should be able to see the whole picture of all streams. Give it some time, here we go. So stream number 3, and the exit temperature of stream number 3 is 403.9. And in the tutorial, you're being said, if done correctly, it should be in the 390 to 410 range. So we have 403.9, so we're good. And then for question number 2, for a guessed water flow rate of 15,000, what is the temperature in degrees Celsius? If done correctly, it should be in the 315 to 325. Okay, so I'm going to change the temperature. I'm going to change the flow rate of stream number 1. So I'm double clicking on stream number 1. I'm going to change it to 15,000 and I'll rerun the simulation. And if it's right, I should get a temperature in the range of 315 to 325. So let's have a look here and see if it's going to work out. But you see, for this case, if I want to set my output temperature to 360, for example, I need to do a trial and error situation until I get the temperature I want. However, if you use a design spec, you can get the exact number immediately. I'm using a design spec, which we're going to try in a second. Let's just have a look here and for question number 2, streams. Again, looking at after it tells you results available and you don't have any errors, you just navigate on the left-hand side, results summary, go to streams, and the temperature is 318, which is between 315 and 325. So it matches. Okay. So now we've answered questions 1 and 2. Let's go back to the tutorial. Okay, so we know that the flow rate of water will achieve a stream 3 temperature of 3. We know that the flow rate of water that will achieve a stream 3 temperature of 360 Celsius will be somewhere between 14,000 and 15,000. But you can see how tedious this is going to be. Of course, if you keep on, doing trial and error, it's going to take forever. So now let's automate this process by using the design spec. Okay. So under simulation tab, we're going to go to flow sheeting, design specs, and we're going to set a new design spec for this case. So just pay attention here. Let's see how we're going to do this. So I'm going to go under flow sheeting, design spec, and I'm going to set a new design spec. Okay. So flow sheeting, I'm going to set a new design spec. I'm going to call it DS1. You can call it water flow rate 1, whatever you want to call it, doesn't matter. DS1 in this case, and we're going to get this window. So I need to define a spec, and I'm going to vary it between some temperature. So in this case, I'm defining a new variable, and this variable I'll call it T3 because I want the outlet temperature of stream number 3 to be fixed. So I'm going to call T3, and it's a stream, right? It's a stream variable in this case, and type here. So actually, let's set it as all. You can set that as stream, doesn't matter, but let's do the general thing where we set it as all. And then the type of variable in this case is a stream variable. And the stream we're interested in is stream number 3. And again, it's a mixed substream, and the variable we're interested in is temperature, and the units is C. So I went to, so in order to set it, to do a design spec, you navigate on the left-hand side here of the tree, you go to flow sheeting options, you go to design spec, you start a new design spec. And under this design spec, I have 3 tabs I need to specify. The first tab, I'm defining the variable I want to control. So in this case, I want to control the temperature of stream number 3 to 360. So I say the variable I want to control is, you define a new variable, set a category all. It could be a block, it could be anything, but in this case, we're just using all. The type, it's a stream variable. The stream we're interested in is stream number 3, and the variable we're interested in is the temperature of the stream. And this should satisfy your define tab. And now we can move on to the next tab, which is the spec. So what does the spec mean? It basically means what's the metric? What metric do you want to control? So in this case, the spec is T3, which is the variable we just defined. The target for this variable is 360 degrees Celsius, which is what we want to achieve. And the tolerance, you can set whatever tolerance you want. I'm going to set it at 0.01. If it doesn't work, we'll make it 0.1, but you can set whatever tolerance you want. So I defined the variable I want to control. I put in the spec for this variable. So I want this variable to be at 360. And what parameter am I going to vary? Right, so now we go to vary. And what parameter will you vary? So let's have a look here. Again, I'm varying a stream variable, right? For stream number 1. And I'm varying the mole flow rate. Okay, so again, this is the spec I set, and I'm going to vary this stream variable, which is the molar flow rate of stream number 1, and I'll change it from 14,000 to 15,000. So basically I'm asking Aspen to have a look between 14,000 and 15,000, look at all the numbers, try out all the numbers, and get me the flow rate which will satisfy this spec, which will make my exit temperature at 360 degrees Celsius. So again, if you want to set a design spec, on the left-hand side here, you go to flow sheeting options, you go to design spec, you set a design spec. We have 3 tabs. First one is define. I'm defining the variable which I want to control. In this case, we call the T3. The type of this variable, it's a stream variable. It's a variable in stream number 3, and it's the temperature. Once you're done with this step, you go to the spec tab, and here you're setting the condition, which is I want the variable T3 to be fixed at 360 or to reach the target of 360 with a tolerance of 0.01 and vary. So in order to do this, you need to give Aspen another variable to change, right? And you set this variable in the vary section. And in this case, it's a stream variable, stream number 1, and I'm varying the flow rate of stream number 1 between 14,000 and 15,000, okay? So after we set the design spec, let's run it and see if we get a result which makes sense. And all these details are specified in the tutorial. You have the screenshots. So you know it makes it easier for you if you want to follow the tutorial itself. Okay, so design spec ran. So everything is blue check, and at the bottom here I have results available. So let me look at the results again. You just expand the tree, click on results. Let's have a look here at the results. So the manipulated variable, the initial value was 15,000, the final value was 14,494.7, and this will achieve a T3 of 360.02. Okay, so the flow rate in order to achieve a 360 degree Celsius temperature of stream number 3 is 14,494. Okay, so if I set stream 1 here, if I go to my main flow sheet and I set the value of stream 1 to be 14494.7, so I go 14494.7, I should get an outlet temperature of 360, and I run it. And then I have a look at the stream results. Give it a second here. You can see that I'm going to get a temperature of 360, 359.999. It's within your tolerance of your calculation. So again, just be aware that the design spec is a very useful tool. So if you're doing building an Aspen simulation for your senior design project or anything like that, and you're not sure about one of the flow rates, but another condition, you can ask Aspen to run sort of an analysis for you to zone in on the best conditions for your process. Okay, so now let's go back to the tutorial and see if there are any questions which have to be answered. What's the flow rate in kilomole per hour of water that exits the heat exchanger at 360 and 20.5 bars? We already found this, so this is the flow rate we found out. Okay, sounds good. So this is part 1 is done. Let's have a look at part 2. So now that we know the stream flow rate, we can design the rest of the system. First, add the remaining streams and blocks into the model according to figure 3.2. So let's do this, and then we'll move on to the next step. So we're looking at figure 3.2, which is all the way up here. So what do I need? I need to add 2 turbines and the condenser for this simulation, right? Okay, let's do this, and then I'm gonna call this 4, 5, and I'm gonna call the output of the condenser 1B. Okay, let's go to Aspen Plus and let's try to do this. So let me close all these tabs right here. And I'm going to have a look at the main flow sheet. Again, if you lose the flow sheet, if you lose anything on the screen, you go to the view tab at the top here, and you can toggle anything you want. You can make the flow sheet disappear, you can make it appear, it doesn't matter. You just toggle everything from the view tab. If you don't find it from the view tab at the top. Okay, so let's have a look here. So I need to add 2 turbines, and I need to add a condenser. Okay, turbines. Where are the turbines? They're here basically, right? Usually a turbine is represented as, on the opposite side, so we're going to use the correct format. So I'm going to drop 2 turbines here, and then I'm going to go to heater, basically add a condenser as well. I like to cascade the turbines this way, but do whatever you want, doesn't matter. Okay, to connect the stream, I'm going to right click on stream number 3, reconnect destination, and I'm going to reconnect it to the inlet of the turbine. Again, make sure you're connecting it to this arrow right here. If it's not connected, you're going to get errors, input incomplete, whatever it is, basically because it's not connected. And then I'm going to click on the material. I'm going to connect the output of this turbine to the input of this turbine. And I'm going to connect the output of this turbine to the inlet of this heat exchanger. And I'm going to connect the output of this heat exchanger right here. Then I'm going to click on escape. And as you can see, this heat exchanger is sort of, is going, the stream is going around it. So I'm going to right click on here, and I'm going to click on rotate icon, flip horizontal, just to make it look better, right? Just to make it look easier. Okay, so now let's rename these turbines and just rename our streams. Okay, so we said this is stream 4. We said this is stream 5. We said this will be 1B, right? This guy right here is the condenser, right? Let's call it condense. CND condense. Here we go. Give it a, forget about the vowels, right? Okay. What else do we need? Turbine 1, turbine 2. So let me just call them turbine 1 and turbine 2. Turb 1, turb 2. Good. So I think now we have everything for this stream, right? Okay, so now let's go back to the tutorial and see what do they want. So we're in part 2, all the way down here. For the turbine models, you'll find them in the model palette. Okay, Aspen Plus using the same model, so it doesn't matter which icon you select, but you can try to get into the habit of choosing the correct icon anyway. Okay, make sure the models use an isentropic turbine and leave the efficiencies as empty. Okay, so let's do this. So I'm gonna make sure that the models use an isentropic turbine and set the efficiency as empty. So I'm gonna click on this guy, turbine 1, double click on it to go to the sheet. And I want it to be isentropic, and I'm gonna leave the efficiencies as empty. Okay, and then I'm gonna go back to the main flow sheet. I'm gonna double click on turbine 2. And you can always navigate to them as well from the tree on the left-hand side, sorry, and you'll get the same thing, but you can always double click on them. And if you double click on them, they all show up here at the top like tabs, Okay, so we set both turbines to isentropic. Let's go back to the tutorial. Let's make a guess at the outlet pressure of the first turbine of 5 bars. Okay, and then you can specify the outlet pressure of the second turbine according to the process diagram in figure 3.2. So let's go to figure 3.2. So I'm gonna guess this as 5 bars, the output of turbine 1, and then I'm gonna put the output of turbine 2 at 1 bar. So let's do this. So the output of turbine 1 will be 5 bars. So main flow sheet, turbine 1, I already have the tab open here. And I'm gonna set the discharge pressure of turbine 1 to be 5 bars. And I'll set the discharge pressure of turbine 2 to be 1 bar. And this should, both of them should have the blue check. So all the inputs are satisfied. Let's go back to the tutorial. So let's make a guess, 5 bars, and okay, we did this. You should be able to handle a condenser already. You already know the requirements for the hot stream and don't know anything about the cold stream. So which block do we use? Assume no pressure drop in the condenser. Okay. So let's go back to the condenser. So what does he want basically? So I know that the output of the condenser, or actually let's go back to the process flow sheet here, to the tutorial, sorry, and just have a look at the figure 3.2. So the output of the condenser has to be 95 Celsius and 1 bar, and the inlet is 1 bar, so there is no pressure drop across the condenser, and the discharge pressure is 95 Celsius, and this should be enough to specify it really. So I'm going to go to the condenser here, I'm going to double click on the condenser, I get the sheet, and we said we want the output temperature to be 95 Celsius, and the pressure drop will be 0. Again, if you want to set a pressure drop, you can either set the pressure to 0, or you can set your correlation parameter to 0. It does not matter. You're going to achieve the same result. Let me, let's go to the tutorial here. Okay, so let's find the page where we were at. So we've finished here, we set the condenser. Tom's tip: in the conversions tab of turbine setup, change valid phases from vapor to vapor liquid. This will allow the model to function properly in case a liquid phase is formed in the output, since the stream will get colder. Okay. So basically, in the turbine, we're going to change it from vapor only to vapor liquid, so that we have steam entering. It's going to cool up significantly. So this helps us control the thermodynamics or calculations, basically. Let's go to turbine here. So again, main flow sheet. Always navigate from the left-hand side, or you can double click. I already have the tab open, so I just select turbine 1. And we said we're changing the, let's see, we said the conversions, right? From vapor only to vapor liquid. And let's just increase it to 200 as well. Just increase your iterations whenever you can. Then do the same for turbine 2. I just navigated using the tabs at the top. You can navigate to turbine 2 by double clicking on it, or by navigating from the left-hand side tree right here. Okay, so I double clicked, I got this tab at the top. I'm gonna go to conversions. Let's make it vapor liquid, and let's increase this to 200 as well. Okay, so we did this. Let me go back to the tutorial and see what do they want. What's the total cooling duty in megawatt required in the condenser when the first turbine has an exit pressure of 5 bars? Okay, so what's the duty of the condenser if we set the exit pressure to be 5 bars, which is what we did? So in order to find it, let's just run the simulation and see what the duty of the condenser will be. So again, to run, you click on run, or you can click on next, and it will tell you all input complete, and then you can see your results. So in this case, results available, so everything seems fine. So in order to get the duty of the condenser, I'm gonna navigate to the condenser from the right-hand side here. So under blocks, I'm looking for condenser, and I'm looking at the condenser results. And I'm getting duty, net duty, but they're all in calories per second. We want it in megawatts. Let me find it in megawatts. So the duty is minus 166.479 megawatts. This is the answer for question number 4. Okay, so we found the cooling duty for this condenser. Let me go back. So this answer for this one was minus 166.479. Finally, we're interested in the total work produced by the system. To find this conveniently, use work streams like heat streams, but different. Add work streams to the outlets of the 2 turbines and the pump. This represents what in reality might be a shaft for a compressor turbine system. to transmit mechanical work or an electrical connection for electrical work. Okay. Okay, and then to get the total work, we can either add them together by hand or have Aspen Plus use a work mixer. Okay, so what this is telling you basically is let's find out the total work being done by the system. And you know, you have turbines, so a turbine is gonna do some work. Basically, it's gonna generate some energy from the steam. You know, steam is gonna drive a turbine, you're gonna get electricity. This electricity could be either mechanical energy, electrical energy, etc. And we can use Aspen to measure this actually. So in this case, we were gonna do this by adding these work streams, right? Okay, so we're gonna go here. 1 second, I just wanna make sure I'm sharing the screen, okay. So how do you add the work streams? You, again, on your model palette on the left-hand side, you have materials. I'm gonna click on the small arrow. I get this work stream here, click it. And I'm looking for the work exiting these units. So I have work exiting the turbine 1, work exiting turbine 2, and I also have work exiting the pump. Let me just calculate it as well as your tutorial wants. And then the tutorial asks you to, I want to find the combined amount of work here. So I can add them by hand. So I can run the simulation and add them by hand, you know, using a calculator. Or alternatively, you can use a mixer unit. And you know, mixer here, this is a mass mixer, stream mixer, as you can see. If you want to get a work mixer, you need to basically expand it by clicking on this arrow right here. And you see here this block called a W mixer, and this is what we're going to use. So I'm looking for a work mixer. This is what I'm going to use. Click on this guy right here, drop him, and you get this big square block, you know, work mixer. And now I'm going to connect these 3 streams as an inlet, and then I'm going to add an outlet as well to this mixer. So right click on this, reconnect destination right here. Same with the second one, reconnect destination right here. Same with the third one, reconnect destination right. And make sure you're connecting it to the actual arrow. Otherwise, you're gonna get wonky results, right? And then after connecting all the inlets or combining them into the mixer, I'm gonna click on the work stream here on the left-hand side of the model palette. And I'm gonna connect an outlet work here. And again, click on escape to get rid of the sticky mouse. And I'm gonna call this total work. Okay, and this is the total work stream for this, from this process. Okay, so now we have our scenario as the tutorial is asking. Let me go back to the tutorial and let's see what do they want. To get the total work and either add them together by hand. Okay, that's what we did. We added the work mixer. Add a third work stream to the outlet of the work mixer to make a stream that has both turbines works combined. Okay, so basically just combine all of them into your mixer. This is what we did. Sorry. On the simulation using the correct water flow rate that resulted from the design spec, that's what we did, and assumed 5-bar outlet pressure in the first turbine. So this, we already have this set up, so we just need to run the simulation. But let's keep in mind what question 5 is asking for. What is the total electricity produced in megawatts by the system when the first turbine has an exit pressure of 5 bars? The negative is Aspen Plus's way of saying that work is produced rather than consumed. So I need to find basically the amount of work being done by my system. Okay, so let me go to my simulation and let's try to figure out this number right here. So I'm looking at this. I need to find out the total work, this result right here. So I'm gonna run my simulation. So again, I'm gonna go to home. I'm gonna run it and see if it gives you any errors or anything. We can always fix it. Okay, so try and find results are available. So let's have a look at the results. So in order to find this total work, You can probably find it from your streams, right? If I click on the results summary, as you can see, I have material, I have heat, and I have work. I'm interested in work. So at the top here, I'm clicking on work. And total work is 10 kilowatt. Anyways, if you want to change it to megawatts, we'll have to navigate. So okay, so your total work is minus 33521 kilowatt. If you want to, I mean, we can make a conversion to megawatt, right? If you want to make a conversion to megawatt, we need to go to the basically click on the stream itself. So if I click on the total work stream, navigating to it from the left-hand side here, I should be able to see the results. So if I click here, click on results. Okay, so again, I can change it to megawatt, but anyways, you can calculate it in megawatts. And you can see that the total power from the system is minus 33 megawatts. So basically this system generates 33 megawatts, just by looping water, using the heat from your reactor, cooling it down, and relatively low flow rate, actually, 15,000 kilomole for 14,400 kilomole per hour can get 33 megawatts. So again, this goes down when designing a process. You don't want to lose energy. You can always generate electricity, generate something useful out of it. Okay. As a result, as a check, the results of Q4 and Q5 should add up to 200 megawatts by an energy balance. Double check to make sure that stream 3 is still at the proper temperature. Okay, so it's telling you that the result of Q4 and Q5 should add up to 200 megawatts. What was Q4? Let's do this check. What's the total cooling duty required in the condenser? So I'm looking at the cooling duty of the condenser and the electricity produced by this guy. Okay, let's have a look here. I need the cooling duty by the condenser. So I'm gonna double click on the condenser here and just select it. I'm gonna click on the results. And the cooling duty in megawatts is minus 166.479. Okay, and your work was minus 33 megawatts, right? So minus 33 minus 166 is minus 200. So this matches what the tutorial is asking for, so it makes sense. Good. Double check to make sure this is at the proper temperature. You can double check it. Next, we want to find the turbine 1 discharge pressure that maximizes our work produced by the turbine. Okay, so this work was achieved by, after we fixed the discharge pressure to 5 bars. However, if we play around with this pressure, maybe we can get more energy out of the system, or we can find the best pressure that will give us the most work. We can't use a design spec to do this because we don't know what the exact power output we want to produce. So we're going to use sensitivity analysis, okay? So this is basically just the guess part of the guess and check. And then the difference between a sensitivity analysis and a design spec is that in a design spec, it's going to run the simulation until it reaches the spec you want, and then it's going to stop. Whereas in a sensitivity analysis, it's just going to run over the entire range. So if you recall in the design spec, it ran until it got to the answer and then it stopped. If we're running a sensitivity analysis, it will just show me all the results, and then I need to select the best condition myself. And you can read the difference here. It's a good tool to have. Please just read it. Try to get an understanding of what's going on. Okay, so I'm going to make a new sensitivity analysis in the model analysis tools, sensitivity. So let's go to our simulation and let's navigate the sensitivity analysis situation. Okay, so I'm going to clean up my tree here. I'm just going to close all of these to make it easier for me to navigate. Once you get more comfortable, you can do whatever you want. And I'm going to do one thing, right? Under model analysis tools, I'm going to create a new sensitivity analysis. So model analysis tools here, sensitivity. I'm going to create a new analysis. You get this window, click on new. Let's leave it as S1, doesn't matter. And then you can follow the pictures in the tutorial. I'm not gonna go back and forth between the tutorial. I'll just do it right here so that it's easier for you to follow, or you can follow it in one step instead of jumping back and forth between these two. Scenarios. So again, we said we're navigating to model analysis tools, sensitivity, new sensitivity, and we'll call it S1. And I'm gonna get this screen right here, right? Let me close that. Okay, I'm gonna get this screen right here. So again, similar idea. I need to define the variable I'm changing. So in this case, I want to change the output of turbine number 2. So if you recall, I want to change the discharge pressure of this turbine to maximize this work, right? This will be what I'm working on in this sensitivity analysis. So let's define this variable. So again, let's call it variable new. Calls it variable 1. So, and again, in this case, it's a block variable, right? Because I'm looking at the discharge pressure of a turbine. So it's a block variable. Let me see if there's a block variable, right? And the block I'm interested in is turbine number 1. And I'm interested in the pressure, right? I'm interested in the output pressure. So I'm gonna go here and select output pressure, or pressure. Yeah, specified outlet pressure, this is what I'm interested in. And the units are in bars, so it's fine. And you need to set your manipulated variable limits. So let's change it from 2 to 25 bars, and with increments of 0.1. Okay, so I wanted to change this variable between 2 and 25 with increments of 0.1, and basically this will be the variable I'm changing in this design spec. So now I need to define something. So I'm going to define a new variable, or this is the variable I'm interested in. So in this case, this variable is, let's define a new variable. Let's call it total work. And this is the variable I'm looking at, right? Total work, right? Let's call it total work. And this is basically the variable I want to maximize. And let's find this variable. So what type is it? It's not really any of it. It's a work power variable, right? So we find work power, and the stream is total work from our flow sheet, and the units, you can leave it as kilowatts. Let's leave it as kilowatts just to follow what the tutorial wants you to do. Okay, so I set the variable I want to change. So I'm changing my turbine outlet pressure from 2 to 25. I'm asking Aspen to calculate the total work at each of these points, and then tabulate is basically what results do you want to look at. Okay, so again, I want to tabulate total work, right? So let's call it total. And be careful in this case because, it's very easy to, make a spelling error and not see the result you want. And we also want total work divided by 1,000, right? Divided by 1,000. Okay. So what I'm telling Aspen is, telling it to please vary the outlet pressure of a turbine from 2 to 25 with increments of 0.1, At each of these points, please calculate the total work leaving the system, and please tabulate column 1. Okay, thank you. You can change them 1 and 2, whatever. Just tabulate the total work and the total work divided by 1,000. So basically, total work in megawatts. Okay, let me have a look at the tutorial, see if it wants anything else. Let me go back to the tutorial right here. So this is what we did. We found the block variable turbine. We set from 2 to 20. If I set it to 25, doesn't matter. We defined the total work W4, and we set these 2 streams. Okay, you can read this at your own pace. And now let's run it and let's have a look at the results. And let's answer these 2 questions. So first of all, let me run the simulation. So again here, let me run it. And this might take some time. Just be patient because it's running a lot of points. And so I get results available with warnings. It's fine, it's because you're running a sensitivity analysis. Sometimes the conditions don't make sense for Aspen, so it's telling you, at these conditions, it doesn't make sense. So some rows completed with warnings. Okay, so this is probably because I set it to 25, which is probably above the saturation point of the steam. So it's telling you you're getting water or whatever, but it's fine. So now let's have a look at the results. So I'm gonna look at the sensitivity analysis. I'm gonna click on the results here. Click on S1, click on input, and I'm gonna click on the results. Summary, and I can see all my results here. Total work divided by 1,000 and total work, and I can see all the results. And as you can see, as my outlet pressure of the first turbine changes from 2 all the way to 25, I'm calculating the work produced by the system. Okay, so now let's have a look at the tutorial. Values, you can, the values of anything. If it's not okay, then there was an error warning, it's fine. You can copy it into Excel, or you can just look. What is the net power produced in megawatts when the discharge pressure is 4.8 bars? Okay. What discharge pressure provides the most power? So let's find out. We want to find the megawatts when the pressure is 4.8, and we want to find the pressure which gives us the most power. Let's go back to the simulation. So the first question is asking what's the work when the discharge pressure is 4.8 bars. Okay, so in this case, the work is minus 33.5 megawatts, or minus 33,000 kilowatts, right? Just be careful, just because it says kilowatts. However, we divided by 1,000, right? So it's kilowatts divided by 1,000, so it's megawatts. Okay, so at the discharge pressure of 4.8, your total work is minus 33 megawatts. And at what pressure do I get the maximum work? Basically the highest negative. So let me have a look here. So it seems to be increasing. I'm just looking at this table. So it's increasing 5.2, and then it's dropping to 5.1 again. So it's somewhere in this region, 5.25. Yeah, so it seems that the maximum discharge pressure of 5.7 bars gives me the maximum amount of work. Let me just have a look here at the bottom. It's minus 32. I'm not interested in this. Minus 33, 1, minus 33, 2, 2, 4, 2, 6. What does 33.5, right? Yeah, so 33.5. So this guy is the highest. This at the discharge pressure, sorry, of 5.7 bars, I get the most work out of my system, which is minus 33.5 megawatts. Okay, good. So we answered this. Then let's see what else do they want. Now, if you're being observant, you'll notice that the very sneaky Aspen Plus add another menu option. Plot menu just appeared, so you can always make a plot, and you can create a plot like this. Okay, so let's try to generate a plot as well. Why not? Okay, so let's have a look here. So which one should we use? What's this guy saying? Wants us to make a results curve. So here, custom. No, custom, cancel. Click on the small bottom arrow. I want to look at the results curve. And turbine pressure, and I just wanted to plot the total work divided by 1,000. You can see 2 lines if you want. It's just going to be messy. So let's generate this plot, and we should get this yes check mark. Yeah, here we go. As you can see, after 20.5 bars, we have a phase change in water. That's why the line stops, having this skewed curve. You can always, if you set it from 2 to 20, you're going to get an identical curve to what you see in the tutorial. Sorry. And as you can see, I was just looking at the maximum work. The maximum work is your most negative point, and your most negative point is somewhere here. Minus 5.7 is what we said. So, I think we got it. Okay. Okay. Lastly, let's update our final simulation using the results from a design spec and the sensitivity block. Okay. So let me go to the tutorial, show you what I'm looking at. Lastly, let's update our final simulation using the results from a design spec and the sensitivity block. So we already have the results from the design spec set, so we just need to update the results from the sensitivity block, which is the discharge pressure of the first turbine. So I'm going to click on the first turbine, and I'm going to set the discharge pressure to 5.7 bars, because this is the point where we had the maximum heat, right? So if I look at the S1 results, if you recall, 5.7 will may give us 5.253, and this is basically the most negative work. Actually, 5.25, 5.26, wait. 5.262 is actually the most negative work, right? 5.262, 5.253. So 5.262 is actually the most negative work. So discharge pressure has to be 5.5. Okay, so let's just set it as 5.5. So let me go to the main flow sheet. I'm going to double click on turbine 1. I'm going to set my discharge pressure to be 5.5 in this case. And let's run the simulation and answer the final few questions in this tutorial. Hopefully all the units work fine, and we just have the same error in the sensitivity analysis. So that's fine. Okay, we just have an error with the sensitivity analysis as we did before, but all our blocks look fine. Okay, so all our results are there. Let's go to the tutorial and see what the last few questions are. What is the pump electricity usage in kilowatts? What's the electricity produced in megawatts by the second turbine? And what's the total electrical efficiency of the final power plant? Okay, power produced divided by total energy input, that's fine. So we're putting in 200 megawatts, and how much power are we generating? We're going to calculate this. And what's the electricity produced by the second turbine? What's the electricity usage by the pump? Okay, let's have a look at these three values. So let me go back to the flow sheet. Let me clean up all these tabs. I'm going to close out all these tabs. Okay. You can always navigate from the tree on the left-hand side, or you can use it. So we want the pump electricity usage. So I'm going to double click on the pump. I'm going to look at, from the left-hand side here, I'm going to click on results. And your pump electricity usage is 187.686 kilowatts. All right, this is your pump electricity usage. This is the answer to question number 8. Question number 9, what is the electricity produced in megawatts by the second turbine? Okay, so I'm looking at the second turbine. Again, I'm going to double click on it. And then on the left-hand side here, I'm going to navigate to results. Sorry, it's the second turbine, not the first turbine. So let me close this tab. Let me go back to my flow sheet. Looking at the second turbine, double click on it. On the left-hand side, I'm going to navigate to results. And what are we looking for? Electricity produced. Let's have a look here. Brake horsepower, power loss, efficiency, mechanical, isentropic. So it's not really giving me the electricity produced by the second turbine. Let's have a look at utility usage. Let's just look for it. Might be somewhere here. So the amount of electricity produced will be your network required. Because it's a negative, it indicates the amount of electricity produced, which is minus 16.977. Alternatively, if you don't want to look at it here, you can always click on this output work stream. So if I double click on S5, which is the output stream leaving second turbine, I'm going to get the same number, just minus 16977 kilowatts, which is the same as, minus 16.9 megawatts, right? And this is the electricity from your second turbine. Finally, what's the total electrical efficiency of the final power plant? Okay, so what's the total electrical efficiency? Power produced divided by total energy input. Okay, so power produced over total energy input. Let me have a look here. So if I look at the system just as a closed system, if I just draw a box around this, the energy input is this guy, which is 200 megawatts. The power produced is this guy, which is, how much is this? Let's have a look here. Which is 33.526 megawatts, right? So your energy efficiency is 33 divided by 200. Okay, and this is your total electrical efficiency of the power plant, right? So I put in there's 200 megawatts available in the hot stream from the reactor. However, I can only extract 33 megawatts of electricity from this process. And this is normal because, you can never achieve 100% efficiency, is not possible. You get about 33 by 200, that's it's about 16% efficiency. That's normal, that's expected, If it's super efficient, maybe you get to 40%, but you shouldn't expect efficiencies much higher than that in a realistic situation. Okay, so this is the end of the tutorial number 3. Please follow the steps. If you have any questions, please come to office hours, send me an email, try to reply as soon as possible. Yeah, just try to absorb this Aspen Plus. I'm gonna start posting the simulation flow sheets as well on Blackboard, so that if you need to have a look at a solved flow sheet, you can do that as well. Thank you very much.